Hi, this is the fourth lesson in electricity, mainly focused on Edexcel, Cambridge, and International Baccalaureate syllabuses. The link for the first three lessons are given in the description part. You can go through it. And a short notes for this lesson is also given in the description part. You can download the notes if you like. Okay, so in this lesson, I mainly focus on circuits, right? Before starting circuits, we should know a law called Kirchhoff's law. There are two different laws, Kirchhoff's first law and Kirchhoff's second law. Okay, what Kirchhoff's first law says? Okay, Kirchhoff's first law states about the conservation of charges. That means on a network at a junction, the total amount of charge approaching the junction per second, that is the current flow, is it? Rate of flow of charge is the current flow when we consider 1 second. So the total amount of charge approaching a junction per second must be equal to total amount of charges leaving the junction per second. Okay, so I can draw a junction like this. The total amount of charge approaching the junction per second is the current flow. So the current approaching the junction is I1, I3, and I4. The current leaving the junction is I2 and I5. So the total current approaching the junction must be equal to total current leaving the junction. The reason, charges cannot be created or destroyed. So the charges should be conserved. So here I can say I1 plus I3, I1 plus I3 plus I4 equal to I2 plus I5. That is the Kirchhoff's first law. Very useful when we are doing parallel circuits, and at the junctions we use this one. Okay, the Kirchhoff's second law is about the conservation of energy, conservation of power, or conservation of energy. That means I already told that the electromotive force is defined as the total work done in 1 Coulomb, total work done in moving 1 Coulomb charge through one complete circuit. So the total work done by the power supply when moving 1 Coulomb charge through one complete circuit is EMF, right? So the work done to move 1 Coulomb charge through the bulb is V3, through the resistor is V2, and the work done to move 1 Coulomb charge through the motor, electric motor, is V1, right? So here you can see, according to the law of conservation of energy, total work done by the power supply is equal to sum of the work done across the components when 1 Coulomb charge flown through them. So that means I can say in a closed circuit, that should be considered. In a closed circuit, the total EMF must be equal to sum of the voltages across the components. So in a closed circuit, total EMF must be equal to sum of the voltages across the components. So in this closed circuit, EMF is equal to V1 plus V2 plus V3. That is the Kirchhoff's second law. Okay, so mainly in this lesson, we are going to learn about uh, circuits. So when there are more than two components, how can we connect them? Either we can connect them either in series or parallel. Okay, before that, you should know that current flow in a circuit is decided by the EMF of the power supply and the total resistance or the resistance of the components. The current flow is not decided by the function of the components. So in circuits, we don't consider whether it's a bulb or motor or whether it's a heater or whatever it is, we don't consider. We consider their resistance. Remember that we never consider the function of the components when we are calculating current, when we are calculating the total resistance. We never consider the functions of the components. We consider only their resistance, because resistance and the EMF decides the current flow, not the function of the components. Okay, so when there are components, more than one components, well, how can we connect those components among them? So they could be connected either in parallel among them or series among them. So when they are connected in parallel among them, that circuit is sometimes called parallel circuit. Circuit is not parallel. The components are connected in parallel among them. Same way, when the components are connected in series among them, that is called series circuit. Sometimes, not all books, some books they call it as series connection, parallel connection. So connection is not series or parallel. The components are connected among them either in parallel or in series, and we consider only their resistance, not the function. Okay, how to identify when we have two components, they are connected with each other? How can we decide whether they are connected in parallel or series? Okay, there are some rules to identify whether they are connected in parallel or series. I'll start with parallel. How can I decide, okay, these two components are connected in parallel among them? Okay, so see the first diagram. Actually, here you can see a bulb, a resistor or heater, same notation. This is the electric motor. Now, when I see these two components, bulb and the resistor, you can see that all components have two terminals except transistor, but transistor is not in your syllabus. Transistor has three terminals, but anyway, it is not in your syllabus. So all the components in your syllabus, we are dealing with two terminals, right? So when we consider the bulb and the resistor, they have two terminals. Now see, the terminals of the bulb is directly connected to a junction. Junction means, you know, junction of a road, there will be many branches, is it? So there will be many branches from a junction. You can see the bulb is directly connected to the junction X and Y. Junction means you can see from that there are many branches. There are many branches. Same way from Y there are three branches. Here also there are three branches. I can draw more branches also. So I drew only three branches, right? So you can see the bulb is directly connected to the junction. The resistor also directly connected to the junction. Same way, the electric motor also directly connected to the junction. So when you think about the bulb and the junction, there are no other components between this terminal and the junction. There are no other terminals. Directly the Y is connected to the junction Y, and the other terminal of the bulb is directly connected to the junction X. When you consider the resistor here, the two terminals are directly connected. I'm using the word directly, carefully notice that. Directly connected to the junction. Same way, here also in electric motor, the two terminals are directly connected to the junction. So, when there are more than one components connected among them like this, if they are directly connected to the junction, then we say those components are connected in parallel among them. Understand? So, for example, if there's another component, something like this, there's another bulb I can call V2. Then I can't say the bulb, this one, if I name this bulb V1, then I can't say V1 and R2 are connected in parallel is a wrong statement, because the terminals of the bulb is not directly connected to the junction. It's directly connected to the junction here. One terminal is directly connected to this junction, and the other terminal is connected to the bulb V2, not to the terminal, not to the junction Y. So I can't say V1 and R2, this resistor and the bulb V1 are in parallel is a wrong statement. Okay, so if you want to say two components are connected in parallel, they must be directly connected across two junctions. Then only we can say they are connected in parallel among them. So here all these three components, bulb, resistor and the electric motor, they are directly connected to the junctions X and Y. Therefore, they are connected in parallel among them. Okay, so how can we decide two compounds are connected in series? Okay, now look at here. When you think about this bulb and the resistor, there are no junction or branches between the bulb and the resistor. The bulb and the resistor are directly connected with each other. Can you see that? They are directly connected with each other. There are no junction or branch between the two components. Okay, so I can say bulb and resistor are connected in series. So when you say two components are connected in series, between them there won't be any junction or branches. Same way, when you consider this and this, how are they connected? there is no component between them. There is no junction or branch between them. So R2 and this electric motor, they are connected in series. There is no junction, no branch. So this electrical resistor and the electric motor, they are connected in series. They are connected in series, no junction, no branch. They are connected in series, no junction, no branch. So I can say all these three are connected in series among them. So simply we can identify if there are no junction branch between two components, they are connected in series. If two components are directly connected across two junctions, then they are connected in parallel among them. Remember, that's very important. You must be able to identify when you see two components, how are they connected. Okay, that's very important. I hope you understood how to identify whether two components are connected in series or parallel. Okay, so here I'm going to get an equivalent resistance. What do you mean by equivalent resistance? Say, for example, here these three components are connected in parallel among them. I already explained how to identify whether they are series or parallel. So they are directly connected across two junctions, X and Y. And I told that the current flow is decided by the resistance, not by the function, right? Okay, so here you can see, normally we take these connecting wires, they don't have any resistance. So wires have no resistance means at all points the potential will be the same. Say for example, if I consider 2 points in this wire, this point and this point, what is the potential difference between these two wires, P1 and P2? If you ask me, the potential difference between these two wires will be equal to 0. There's no potential difference between two wires because there is no resistance. V equal IR. So there is current flow, but the resistance between these 2 points is equal to 0 in the wire. So R equals 0 means potential difference is equal to 0. So then you can ask me how the electrons are flowing, the potential difference 0. Potential difference is 0 between any 2 points on the wire. But when we consider the potential across the terminals of the power supply, there will be potential difference. So because of the potential difference across the terminals, there is current flow, right? But when you think about 2 points on a wire, there is no potential difference because we take the resistance of the wires 0, but practically there will be small resistance. But in your syllabus, we normally take wires have no resistance in circuit. So when we consider 2 points on a wire, there is no potential difference, that will be equal to 0. Right, so the potential across the terminals X and Y, so there is no potential difference across any 2 points of the wire. So potential across X and Y, that means if I connect a voltmeter across X and Y, or if I slightly move the terminals of the voltmeter here, it will read the same value because this wire, whether I am connecting the voltmeter to point Y and X, or this point and this point, if I am connecting the voltmeter to this point and this point, the reading will be the same because this portion of the wire will not change the reading of the voltmeter because that portion of the wire has no resistance. So I can say voltage across the junction XY will be same as, even if I connect it here, or even if I connect the two terminals. Imagine these are the two fingers, I assume as the two terminals of the voltmeter. So if I connect the voltmeter across X and Y, or here, the reading will be the same, or here, reading will be the same, reading will be the same. Finally, the reading will be the same. That will be the voltage across the power supply, that is the electromotive force. So I can say simply the voltage across the junction XY will be same as the voltage across the terminals of the power supply, that is the EMF. Same way, now look at here. If I connect the voltmeter across X and Y, that is same as voltage across the EMF, voltage of the power supply, which is EMF. And see here, if I move the terminals of the voltmeter even slightly, little more here, the reading same, reading same, reading same. So voltage across the bulb is same as voltage across the junction. So voltage across the bulb is same as voltage across the junction. That will be same as the voltage across the power supply. Same way, voltage across the resistor, same as voltage across the junction. voltage across the electric motor also same as voltage across the junction. So these three components are directly connected across the junction. So voltage across the bulb is same as the voltage across the junction. Same way, voltage across the resistor also same as voltage across the junction. Voltage across the electric motor is also voltage across the junction. But in this circuit, voltage across the junction is equal to EMF of the power supply. I hope you understood, because these wires have no resistance. So whether we connect a voltmeter here or slightly here or here, the reading will be the same. There is no change in voltage because of the wire. Wire has no resistance. Okay, so these three components are connected in parallel, and the voltage across them will be same as voltage across the junction XY. So if I say voltage across the junction VXY, that will be the voltage across the bulb, that will be the voltage across the resistor, and that will be the voltage across the motor. But in this circuit, voltage across the junction is same as the EMF. Okay, right. So the current flow in this circuit, we know that current comes out of the positive terminal. Actually, the electrons are flowing out of the negative terminal, but you know, conventional sign, the direction of the current flow is taken as opposite to the flow of direction of electrons. So the current is flowing this direction. So the current comes here, will divide into three parts because of the Kirchhoff's first law. So current through this one is I1, through this one is I2, through this is I3, right? So that's the way current will divide. Higher the resistance, lower the current. Right. Now, what is equivalent resistance? Okay, I told that earlier. We never deal with the function. We consider only the resistance of the components, not the function of the component. So we know that these three are different type of components. They have different functions, but the current flow I is decided by their resistance. Now, equivalent resistance means if I remove all these three components, and across the junction, imagine if I remove all these three from the circuit, and across the junction, if I can connect a resistor R, and when I connect the resistor R across the junction XY, when I connect it, if I get the same current I, the current which is coming out of the power supply is I. So when I remove all these three from the circuit, and across XY, when I connect a resistor R, if I get the same current I, then I can call this R is equivalent resistance of these three components. Understand? That's the meaning of equivalent resistance. So don't say this resistor will have the functions of them. No, they don't. It won't have the same function as this one. They are completely different functions. But we consider the resistance. If I remove all these three components, and when I connect a resistor R across XY, the same power supply, if I get the same current as here, then I can call this resistance R is equivalent to the total resistance, equivalent to total resistance. So total does not mean just adding. We are going to get a different format, but I can say this resistance R is equivalent to the equivalent resistance of these components. So what's the relationship between R and R1, R2, R3? How can I get a relationship? Okay, I'm going to derive the relationship now. Okay, so I already told that voltage across the bulb is same as the voltage across the junction, that is same as the EMF. So I can use V equal IR for the bulb, right? If I use V equal IR for the bulb, the voltage across the bulb is the voltage across the junction, that is same as the voltage across the terminals of the power supply, which is EMF. So V will be EMF for the bulb, current through that is I1, R1 is the resistance of the bulb, so I will be EMF over R1. Same way for the resistor, if I write, for the resistor, I can say the voltage across it same as XY, that is equal to EMF. Voltage across this one is EMF. current is I2 times R2. So I2 will be EMF over R2. Okay, same for the motor if I write. If I consider for the motor what will happen, same way I can write I3 will be the voltage across the motor also, same as voltage across the junction, that is the EMF. So I3 will be EMF over R3. Okay. I know, according to Kirchhoff's first law, I equal I1 plus I2 plus I3. So I equal I1 plus I2 plus I3. Right. Now, when I consider the equivalent resistance, that means a resistor which is connected across junction after removing that, and I'm getting the same current there. That's the reason I call this as equivalent resistance of these three. So when I consider this circuit, equivalent circuit, where the current flow is I, the resistance is R. So here I can say V equal IR if I use for this equivalent resistance. I can say the voltage across it is EMF. If I connect a voltmeter across it, that will be same as the EMF. So equal to I times R. So I is equal to EMF over R. I can call this equation 2, this one equation 1. Okay, when you consider equation 1 and 2, the left side is I, same. Therefore, the right sides must be same. So when I consider these two equations, right side EMF over R equal, instead of I1, I can substitute EMF over R1. Instead of I2, I can substitute EMF over R2. Same way, EMF over R3. So all the EMF will get cancelled. Finally, 1 over R equal 1 over R1 plus 1 over R2 plus 1 over R3. So here R is the equivalent resistance, and R1, R2, R3 are connected in parallel among them. So the equivalent resistance of these three components, they have resistance R1, R2, R3. So the equivalent resistance will be equal to 1 over R equal 1 over R1 plus 1 over R2 plus 1 over R3. So this is called equivalent resistance of the parallel connection. You can ask him, so if I don't consider this one, if I want to find the equivalent resistance of bulb and the resistor, okay, then you can say 1 over R equal 1 over R1 plus 1 over R2 because they are connected in parallel. So I don't need to consider always the total equivalent resistance. I can consider just two components and I can find the equivalent resistance of those two components. Or you might need to find the equivalent resistance of only the bulb and motor. Some reason you are finding the equivalent resistance of bulb and motor, then I can say the equivalent resistance of bulb and motor is equal to 1 over R. Okay, 1 over R is the equivalent resistance of bulb and motor, that is equal to 1 over R1 plus 1 over R3. Like that I can find the equivalent resistance of any two or more than two components. Those are connected in parallel among them. Okay, so we'll do an example. A bulb and a resistor, they are connected in parallel with the power supply. The resistance of the bulb is 20 ohms. Resistance of the resistor is 10 ohms. Find the equivalent resistance. So we can find like this equivalent resistance of these components, or find the total resistance of the circuit. Both refers the same, right? So I can say 1 over R equal, they are connected in parallel because they are directly connected to the junctions. 1 over R equal 1 over 20 plus 1 over 10. Find the R. You know how to find it. Find the R. So you will see R equal 6.67 ohms. Okay, now look at here. The resistance of the bulb is 20, this is 10. You can see the equivalent resistance is lower than the lowest of these two components. Those are connected in parallel. So you can see that is 6.67. That is lower than the lowest. Among them, the lowest is 10 ohms. Say 20 and 10. So 10 is the lowest among these two resistors, but the equivalent will be lower than the lowest in the component. Okay, so that is one of the conclusion we can say. When components are connected in parallel among them, the equivalent resistance will become lower than the lowest resistance in the component, lowest resistance in the series connection, parallel connection, right? So the equivalent resistance will be lower than the lowest. Okay, if I connect one more resistance in parallel, say for example, I'm going to connect another resistor, say something like I'm connecting a motor which has resistance 30 ohms. What will happen to the equivalent resistance now? So now the equivalent resistance 1 over R equal 1 over 20 plus 1 over 30 plus 1 over 10. Find the equivalent of it. You will get another conclusion from this. Okay, you will get 5.45 ohms. See, when I add another component that has resistance 30 ohms, that also in parallel with the earlier two components, bulb and resistor. Now the equivalent resistance of the three components, or the total resistance of the circuit, is dropping further. Earlier it was 6.67, now it has become 5.45. So I can give the second conclusion about the parallel connection. That is, when more and more components are connected in parallel, the equivalent resistance will decrease further and further. Understand? So, two conclusions I can say. When components are connected in parallel among them, the equivalent resistance will be lower than the lowest resistance of the components in parallel. The second conclusion I can say, when more and more components are connected in parallel, the equivalent resistance will decrease further and further. Why the equivalent resistance is decreasing further and further? If I connect one more resistance here, those who are interested can try something like that. Connect another resistor in parallel here, something like this. I draw line something like this. Another resistance in parallel connected something like another bulb which has resistance 100 ohms. Whatever it is, you will get lower than this one. So why is it like that? The reason is, when I add more and more components in parallel, the path for the current flow is increasing. Now earlier, when I had only two components, the path for the current, only two, current which comes here, the electrons, they can flow only through these two paths. When I add the next one, I am increasing the path for the current to flow or for the electron to flow. So when I increase the path, more electrons can come from here, no? From the power supply, it can pump more electrons per second. So more path means more electrons can be pumped out from the power supply, means rate of flow of electrons from the power supply will increase. That means current will increase. So current from the power supply increasing means the equivalent resistance of the circuit is decreasing. That's the reason for decrease in equivalent resistance when more and more components are connected in parallel. Okay, just a simple question example. Power supply which has EMF 12 volt. EMF 12 volt means that's the voltage across its terminals. 12 volt is connected across two components. They are connected in parallel among them because they are directly connected across the junctions. So the bulb, current through the bulb is 0.6 amperes, and the current from the power supply is 1.5 ampere. Current from the power supply is 1.5 ampere. So first part, find the resistance of the bulb. So we know that we normally take these connecting resistors have no resistance. So voltage across the bulb is same as the voltage across the junction, because no voltage, if I consider 2 points on the wire, the voltage across the 2 points on the wire will be 0 because they have no resistance. So voltage across the bulb, if I connect a voltmeter here, the reading what it shows is same as the voltage across the junction, that is same as the voltage across the power supply. So I can say voltage across the bulb in this circuit is equal to 12 volt, that is EMF. So I can use V equal IR for the bulb. So voltage across the bulb is 12. Current flow through the bulb is given 0.6 amperes times R1. I'll call the resistance of the bulb R1. So R1 will be equal to 12 divided by 0.6, that is 20 ohms. Second part, find the current through the resistor R. So there's a resistor or heater R. Okay, we know according to Kirchhoff's first law, this current will split through this one and this one. I can call this current I2. So I can say 0.6 plus I2 is equal to 1.5. So I2 is equal to 0.9 amperes. That's the current through the resistor R. See, I am not using 1 over R equal 1 over R1, 1 over. Not necessary. If necessary, only use that equation, right? Otherwise, I can solve the questions without using the equivalent resistance equation 1 over R equal 1 over R1 plus 1 over R2. If necessary, I will use it. But so far, I don't need that, right? Third one also, find the resistance R. So that also, I'm not going to use it. Third one, find the resistance R. So I know the current through the resistance R, that I found it 0.9. The voltage across R also same as the voltage across the junction, that is 12 volt. So I can use V equal IR for the resistor. So voltage across it is 12. Current through that is 0.9 into R. Find the R. 12 divided by 0.9. You will get 40 over 3, that is 13.33 ohms. Right. Now, if you want to use, if you like to use 1 over R format, okay, some students, they do like this. So you note down the final answer, 13.33. To find the final answer, can't I use 1 over R equal 1 over R1, 1 over R2, that format? Yes, you can use, right? How to use it? Now look at here, I'll do that way also. I'll get the same answer, this one. So you can see that the current flow from the power supply is 1.5. The EMF of the power supply is 12. So I can imagine the circuit like this. So this is the power supply, 12 volt. And the equivalent resistance of the bulb and this one, the resistor R, if I say these are the junctions X and Y, so I can imagine across the junction X and Y, an equivalent resistance R node is connected. Okay. Right. So current flow through R node will be 1.5 amperes. 1.5 ampere is the current flow through the equivalent resistance R node. I'm going to find the R node. That will be actually the third. What I did is easy method, right? But anyway, I'm doing the same thing again by using 1 over R equal 1 over R1, 1 over R2 format, right? Okay. So I'll find the equivalent resistance. The voltage across R node is, you know, if I connect a voltmeter, that it is same as 12 volt. So V equal IR, I'm going to use for the equivalent resistance. Voltage is 12, current is 1.5 into R naught. Find the R naught. So R naught will be 12 divided by 1.5. You will get 8. 8 is the equivalent resistance of these two components. Now I can see 1 over R naught equal 1 over R1 plus 1 over R. I can call it as R2 if I want. I can call it as R. I'll just put it 1 over R. 1 over R naught is 1 over 8 equal 1 over R1. We found R1 in the first part, that is 20 ohms. 1 over 20 plus 1 over. You can see this is long step, but anyway I can find it. Find the R from here. 1 over 8 minus 1 over 20, then solve it and take the reciprocal. You will get the same answer as what we got earlier for the third part. You will get 13.33 here also. So the answer is the same, but what I did in the previous method is easier method, is it? Right. So that means it's not necessary to use 1 over R equal 1 over R1 plus 1 over R2, that format every time. Depending on the question, depending on the need, we will use it. Sometimes without using that equation, we will be able to find the required unknown things in the question, right? Okay, so here I'm going to get an relationship for the equivalent resistance of components when they are connected in series to their individual resistances. Say, for example, here the bulb, resistor, motor, they are connected in series. How do I know they are connected in series? There are no junction or branch between these two. So that means this and this are connected in series. Same way when I consider these two, there is no junction or branch, so these two are connected in series. Okay, so the resistance of this one is R1, resistance of this R2, R3, motor, the resistance. So they will have the same current because current has no chance of dividing anywhere. So the same current will flow through all the three components. Since they have different resistance, they will have different voltage across them. V equal IR, I is the same, but R are different. So the V1, V2, V3 will be different. If they have the same resistance, they will have the same voltage across them. When you think about the Kirchhoff's second law, V1 plus V2 plus V3 must be equal to EMF. Okay, so equivalent resistance of these three components, I told the current flow is decided by the resistance, not by the function. So when I think about the equivalent resistance of these three components, now I can replace these three components by a resistor which has resistance R. When I connect it to the same power supply, if I connect the same current I here, that means I can say this resistance is equivalent to resistance of R1, R2 and R3 together, right? So what's the relationship between this R and each of these individual resistances? Okay, we are going to find it now, the relationship. So I can say V1 is equal to IR1 if I use V equal IR for the bulb. For this one, if I use, I can say V2 is equal to IR2. Same way, V3 is equal to IR3. I know that according to Kirchhoff's second law, if I use Kirchhoff's second law, I can say V1 plus V2 plus V3 equal to EMF. So instead of V1, I can say IR1. Instead of V2, IR2 plus IR3 equal to EMF. Let it be first equation. Now, when I think about the equivalent resistance, I told the meaning of equivalent resistance. So the voltage across the equivalent resistance will be EMF. Current flow is same as this current, then only I can call this resistance as equivalent to total of them. So here if I use V equal IR for the equivalent resistance, V equal IR. So V equal IR I am going to use for the equivalent resistance. Voltage across the equivalent resistance is EMF, current I into R. Second equation. Now compare these two equations. The both equations have EMF, EMF. These two are the same. I can write other way if you want. EMF is IR is equal to E. I'll take this as the equation 2. So you can see when you consider these two equations, EMF, EMF is the same. So right hand side same means left hand side should be the same. So that means IR equal IR1 plus IR2 plus IR3. All the I will get cancelled. So R equal R1 plus R2 plus R3. So when components are connected in series, they will be just added. That will give the equivalent resistance. So you know that when you are just adding, the equivalent resistance will become more than any of these resistors. But in parallel circuit, the other way, equivalent resistance will be lower than the lowest resistance of the circuit. But here the equivalent resistance will be just addition. So it will be more than the resistance of any of these resistors, any of these resistance. Okay, just we'll do a simple question again. Okay, so this is a simple circuit, a power supply which has EMF 16 volt is connected to a bulb of resistance 10 ohm, motor of resistance 16 ohm, and a resistor of 20 ohms. So the first part, how are they? The bulb and the motor. Bulb and motor are connected in series or parallel. How are they connected? How to find it? Are they connected in series or are they connected in parallel? So most of the students, they tell they are connected in series because they say they are connected on one line. Right, we'll see whether they are connected in series or parallel. Okay, when you think about the motor and the bulb, are they connected in series? No, they are not in series because there's a junction. You can see there's a branch and a junction. So from, I can imagine this junction, I can name it X. So when you see the X, from that X, there's a branch is there. So that means they are not in series. So I told that if you say two components are in series, there should not be any junction or branch between those two components. There's a junction and a branch from that junction between bulb and the motor. Therefore, bulb and motor are not connected in series. So they are not in series. Okay, so are they connected in parallel? What's the condition to say they are in parallel? They should be directly connected across the junctions. You can see this is a junction and there is another junction here. You can see Y. Okay, so the bulb, when you consider, one terminal of the bulb is directly connected to the junction. The other terminal is connected to the power supply, not to the junction Y. But when you think about the motor, its one terminal is connected to the junction X, the other one is also connected to the next junction. So I can say the motor is directly connected across the junction X and junction Y, but the bulb, only one terminal is connected to the junction S, not the other terminal. The other terminal is connected to the bulb power supply. So motor and the bulb are not in parallel. If they want to be in parallel, for both of them, their both terminals must be connected across the same junction directly. But here bulb is connected to junction X, but the other terminal to the power supply. Therefore, bulb and motor, they are not in parallel also. So how are they connected? That has no proper name or anything. They are neither. They are not connected in series and not connected in parallel. So I can't solve these two components. First, I can't use R equal R1 plus R2. No, I can't use it. Or I can't use 1 over R equal 1 over R1, 1 over R2 for these two resistors because they are not in series, not in parallel. Okay, so now we'll see this circuit again. How are they connected? Bulb and the 20 ohm resistor, are they connected in series or parallel? Again, the same argument. You can see when you consider bulb and the 20 ohm resistor, there's a junction. From that junction, there's a branch going to motor. So they are not in series. If they are connected in series, there should not be any junction or branch between those two components. So they are not in series. Okay, are they connected in parallel then? Okay, the 20 ohm resistor is directly connected across X and Y. X and Y are the two junctions. Again, the bulb, one terminal is connected to X, but the other one is not connected to Y. So bulb and 20 ohm resistor are not in parallel also. So they are not in series, not in parallel. So I can't solve these two resistors directly first. Okay, so because they are not in series, not in parallel, we don't have any equation for such situation. Okay, now the same circuit again. The third question, I can say, how motor and the 20 ohm resistor, how are they connected? Now you can see that motor, you can see directly the two terminals of the motor directly connected to junction X and junction Y. So the Y is bending, but this wire is directly, there is no component here. So the next terminal of the motor is directly connected to Y. So motor is directly connected across X and Y. When you see the 20 ohm resistor, that also directly connected across X and Y. Therefore, the 20 ohm resistor and the motor are directly connected in parallel. They are connected in parallel. Okay, so I can solve and find the equivalent resistance of 20 ohms and 16 ohms by using 1 over R equal 1 over R1 plus 1 over R2. So next question is, they can ask you to find the equivalent resistance of this circuit. So we found it. These two are connected in parallel among them, right? So since they are connected in parallel, I can use the equation 1 over R equal 1 over R1 plus 1 over R2 format, right? So the fourth question is find the equivalent resistance of the circuit. Fourth part, find the total resistance or find the resistance of the circuit. Okay, how can I find it? First, I consider these two. They are connected in parallel. So I can use 1 over R equal 1 over 20 plus 1 over 16. Find the R. So that will be 8.89 ohms. Where should I connect the equivalent resistance of these two? I should connect it across the junction. So I can redraw the same circuit like this. So I told that we never consider the function. We are going to find the total resistance of the circuit. That's all. So I am going to replace these two resistances, 20 and 16, by 8.89. Where should I connect it? It must be connected across the junction. I told that when I was deriving the equivalent resistance. The equivalent resistance should be connected across the junction, right? So I can replace this like this way. So the bulb is still there. Its resistance is 10 ohms. And this is the X. So across the X, I am connecting the actually I am not connecting, I imagine that I am connecting the equivalent resistance 8.89 ohm, and this is the junction Y. So these two are replaced, the resistance of these two, actually the components are not replaced. I imagine the equivalent resistance of these two are connected 8.89 here. Now you can see this 8.89 and 10 ohm. How are they connected? They are in series. You can see there is no junction or branch between the bulb and the equivalent resistance of these two. I connected across the junction. There is no junction or branch. So they are connected in series, right? So I solved these two and I got the equivalent resistance this much. So the equivalent of the bulb and this one, now I can say the final resistance, the total resistance of the circuit R naught is equal to, they are connected in series, so that will be just added R1 plus R2. So 10 plus 8.89, that will be 18.89 ohms. That is the equivalent resistance of the circuit. Okay, so we found the equivalent resistance of the circuit now. Okay, so I can find the current through the power supply by using equivalent resistance. So like that, I will do more challenging questions in my next lesson, that is lesson 5. Okay, in my 5th lesson, I will do more questions. How to find the current through each and every components, how to find the voltage, everything I'll do that in the 5th lesson. Okay, so that's the end of 4th lesson. I'll continue that in the 5th lesson. Bye.